and thanks for joining us. This is another Robe talk. It's become very popular. Thanks all the speakers as well as your participations. ARMA, American Rock Mechanics Association Hydraulic Fracturing Community, which represents 850 members now from 215 international organizations. We're rolling out this series, Robe Talk series, to help connect, entertain, as well as stimulate technical professional when we all practicing social distancing at home. As people start going back to offices, and we basically going to hold this series once a week, every Wednesday morning, 10 to 11, in the month of May, as well as in the month of June. And today it is our pleasure and honor to introduce our technical committee member on hydraulic fracturing, Branko Damjanac from Itasca, going to share the modeling of stimulation and production from Enhanced Geothermal Systems. For the folks who are not familiar, especially new to hydraulic fracturing community, this community is multidisciplinary community. Not only has petroleum, but also we have large members, a number of members from geothermal field and other energy field as well. Hydraulic fracturing is centerpiece of all the fields that we involved. That's a common why we call it the hydraulic fracturing community. So today you're going to see the geothermal side, which is very exciting actually. Especially for hydraulic fracturing guys. If you want to find a second job, this might be your second opportunity. But nevertheless, in the technical committee on hydraulic fracturing, we have 13 members. Half of them actually with a strong geothermal background. And the next year, ARMA, American Rock Mechanics Association, will hold annual symposium in Houston, Texas, Houston, in July. Hopefully everything will be okay by that time. We actually have added another technical track besides petroleum, civil, mining, interdiscipline. We have added a geothermal track to the symposium. So you're going to see a lot of geothermal papers next year in Houston. So today is perfect start of this topic for the geothermal. I think many of you probably know Branko more than I do. He has been around for quite a while. Got his PhD in University of Minnesota, the cradle of American rock mechanics. And he more than 30 years, over 30 years. That's it. I thought more than 30 years. In industry, in the industry as well as family. He has been working on many interesting projects, including the famous Yucca Mountain projects, as well as right now leading the Itasca efforts on the fundamental study or viability of enhanced geothermal system funded by DOE. And with that, I think I just, many of you familiar with this, but I just reiterate. All the Robe talks are carry-out technical talk provided by those volunteer speakers. We are all grateful for their efforts. We do not actually require at all any release from any speaker. Over the past, some of the speakers have kindly released their recording or presentations. Some of them may not be able to share. beyond this meeting. We appreciate your understanding as well as your cooperation as well. We also ask you not to forward the meeting invite to other people. If other people interested, please let them send me an email, and I will register them. This is mainly from legal and copyright view, and we need to follow the ARMA guideline as well. Hopefully you will understand that. And also, we have 45 minutes. If you have questions, please feel free to type in the chat window, and we just figure out where the chat window before the meeting. Branko will address them after his talk. We have 45 minutes up to 1 hour. Normally speakers take 30 plus minutes and then address the questions in the rest. If the question are so many that speaker cannot finish addressing them or address them within the time frame, I'm sure Branko will follow up afterwards. And like I said, please not take any pictures or recordings yourself. We will release if anything that come out. With that, I think Branko, feel free to take over, and let's start the presentation. Thank you.
Okay, thank you, Gang, for introduction, and I also like to thank ARMA, Gang, and Andy Banger for inviting me to give this talk. So I'll be talking about modeling of stimulation and production from enhanced geothermal systems, and the result that I'm going to present today were obtained as part of the study funded by DOE and managed by Sandia National Laboratories. The objective of that study was basically to investigate if enhanced geothermal systems are commercially viable. I'd like to acknowledge two of my colleagues, Azadeh Riahi, who actually carried out all of the simulations that were used to produce results that I'm going to present today, and Jason Furtney, who actually implemented a numerical scheme that allowed us to simulate advective heat transport that was coupled with coupled hydromechanical model to simulate deformation and flow in fractured rock masses. And this coupled hydromechanical model is part of the one of the commercial Itasca codes that we used in this study. So I'll start the presentation with figures showing contours of temperature on a map of continental United States at depths of 3.5, 6.5, and 10 kilometers. And the color scale is not clear. I'll try to help you. The purple is 300 degrees C, and the yellow is 150 degrees C. These pictures were taken from the report, which is titled "The Future of Geothermal Energy" by Jeff Tester, and the quote from the same report is basically saying that EGS resource base is enormous, roughly 130,000 times the current annual consumption of primary energy in the United States. However, the problem is that almost all of this energy or heat is stored in low porosity, low permeability crystalline rock masses. So the question is it possible to create commercially viable power plants? Basically, 5 megawatts electric equivalent power plants, which are based on heat extraction from such formations. this condition of 5 megawatts can be also expressed. Can we circulate the water through these reservoirs at the rate of 80 to 100 kilograms per second? But then also that if we circulate the water, the temperature of the produced water doesn't decrease more than 2 degrees Celsius per year. The condition of flow rate basically requires that these formations need to be stimulated or engineered. So we need to stimulate these formations to increase their permeability. Unfortunately, these two criteria of flow rate and limit on decrease in temperature are competing with each other. Because typically, it is not a problem to increase the flow rate. However, usually that increase of flow rate occurs as a consequence of localization of the flow along a single fracture or a fault, resulting then during the production phase in relatively fast decrease in the temperature as a consequence of the cooling of the skin of that structure. So here on the right side, I show a cartoon illustrating one potential design of EGS. So EGS are located at depths of approximately 3 to 10 kilometers in a crystalline formations. So basically we need 2 wells. One is injection well, and then the other is production well. And then what is in between is this kind of hatched area which attempts to represent desired way of stimulation of these reservoir, where we kind of create a large number of interconnected fractures. So instead of creating single localized flow path, we create actually a network of these fractures, which provides kind of uniform increase in permeability over volume, and hopefully provide a large surface area through which the fluid can percolate. And then consequently, instead of cooling the skin of single fracture, we can actually obtain this sweep of heat going from the injection well towards the production well. So here is the list of different EGS projects carried out around the world. And I think Fenton Hills in 1970 was probably the first one. You can correct me if I'm wrong, but I think none of these projects actually met the goal of 5 megawatts energy production. So the objective of the project that we were involved in was using a physics-based model that correctly represent discrete nature of the fractured reservoirs. Can we prove that these EGS can be economically viable, or under which conditions EGS can achieve this target of 5 megawatts of equivalent electric energy? So we basically investigated and used numerical model to determine what are the favorable in situ conditions for EGS. And then furthermore, given favorable in situ conditions, we try to find out what would be the optimum design of EGS. So we basically look at the orientation, relative position of injection and production well, different completion designs, look at open hole versus cased boreholes. Then look at injection history, including do we want to create hydraulic fracture, or we just want to rely on simulation of the discrete fracture network by hydro shearing. Furthermore, we look at viscosity and a number of different other operational parameters. So besides the need to kind of meet 2 competing criteria, which is given flow rate, but then also a condition that the temperature of produced water doesn't cool down, too fast. The other challenges with design of AGS is that these formations are a relatively large depth, between 3 and 10 kilometers, and we usually have limited access, 1 or 2 boreholes. So we are dealing with relatively large uncertainty and also the spatial variability of the relevant in situ fields like mechanical, hydrological, thermal, and also uncertainty and heterogeneity of associated properties. In addition, both stimulation and production from EGS involves a number of complex processes, starting with chemical, thermal, hydromechanical, and all these processes are actually coupled with each other. So we can stimulate the reservoir in different ways. One way would be actually to create hydraulic fractures, the way it's actually done by oil and gas industry. The challenge or issue with using hydraulic fractures is that they either need to be propped for a relatively long time under conditions of high temperatures, larger temperatures that you would typically encounter in oil and gas reservoir, or actually open or those or generate sufficient pressures during production to kind of reopen those hydraulic fractures. The second option is not acceptable because it defeats purpose, because the energy required to keep those fractures open probably would be more than what would be produced. So another option of stimulating the AGS is basically to try to increase the permeability of pre-existing fracture network or discrete fracture network or DFN. So if you want to base our design on stimulation of DFN, we of course need to have good understanding of that DFN, including density, connectivity, fracture site distribution, orientation, and so on. And then in addition to that, we need to know how to predict or model the response of the DFN to perturbation created by fluid injection during stimulation, but then also during the operation or heat production. So in our opinion, in order to represent correctly hydromechanical, thermal hydromechanical response of the DFN during operation, design and operation of EGS on relevant time and length scale, it is actually necessary to represent these fractures explicitly, because the response of DFN cannot be correctly approximated using a continuum approach. The bottom line is that the main reason that number of these projects, EGS projects, didn't succeed was basically localization of the deformation and flow. So if you're talking about the DFN, by the nature, the problem becomes three-dimensional. Unfortunately, simulation of three-dimensional problems with exclusive representation of this DFN becomes very computationally demanding. And in this study, we wanted to carry out a large number of sensitivities, and we want to be able to carry out those sensitivities relatively quickly. So understanding the limitation, so in the end, we decided to actually carry out these analysis in 2D. And we realized the limitation of this two-dimensional approximation. However, we believe that even in 2D, we were able to reproduce correct qualitative trends. And also towards the end of the project, we did some limited 3D analysis to basically confirm that the 2D models and that obtained trends are correct and reasonable. So we carried out analysis using UDEC, which is two-dimensional distinct element code. It represents the fractured rock mass as assembly of polygonal blocks, which are separated by joints. Some of these joints can be glued together. The model can simulate fully coupled hydromechanical fracture flow, basically a fracture flow coupled with deformation of the blocks, allowing fractures to open and slip, potentially propagate. So the conceptual model that we analyzed is kind of illustrated in these pictures here. So we assume that the reservoir is 2.5 kilometers deep. The thickness of the reservoir is 350 meters. The dominant fractures are vertical, and the UDEC model represents the horizontal cross section. So the geometry of the UDEC model is shown here. The size of the model is 2 kilometers edge length, and the discrete fractures are explicitly represented in the box inside, in the middle of the model, with 1 kilometer edge length. So the first step in the analysis of EGS is stimulation phase. So in this step, we basically use the model to predict increase stimulation of the reservoir by fluid injection. So stimulation phase was carried out as just hydromechanical coupled model. So considering the relatively short injection time, which is typically between 120 hours, we assume that the effect of temperature change and thermal coupling in the stimulation phase can be neglected. So the model is kind of illustrated here. The green line segments represent discrete fracture. The fluid is injected in the middle of the model, and we also provided one cut which is perpendicular to the minimum horizontal principal stress to accommodate potential propagation of the hydraulic fracture. So so what is the mechanism of stimulation of pre-existing fracture network? So the typical fracture geometry is illustrated in this plot on the left side. So we know that the fractures are typically rough, and that slip on a fracture results also in their dilation and opening as a result of this roughness, and the fracture surfaces riding on top of each other. So nice thing about this effect is that it results in self-propping or permanent irreversible permeability change. Now, the fractures in a UDEC model are represented as smooth surfaces, and those surfaces so these surfaces can slip, and the condition for the slip is governed by a Coulomb slip law, where the shear resistance is function of the effective normal stress. Basically, the idea here is by fluid injection, we increase the pore pressure, which results in reduction in effective stress and overall shear strength and potential slip of the fracture. So that's why this entire process is called hydroshearing. So the fractures in UDEC are represented as smooth surfaces. However, the model does implement this conceptual model, which is illustrated as a sawtooth fracture surface, where as a result of slip, the fractures dilate and open, and this entire process of dilation is implemented phenomenologically and controlled by a parameter which is called dilation angle. So in order to cause a fracture to slip, we also need to have some shear stress on the fractures. In order to have a shear stress on a fractures, the in situ stress state need to have some kind of deviatory component. But not only that, the fractures need to be at some oblique angle relative to the in situ principal stresses. So in order to have some shear stresses on the fracture. And here is kind of illustrated a typical stress profile as a function of depth. This is taken from a presentation by Professor J.C. Rogier. So up to depths of 100 feet, we have some kind of thrust faulting regime, and then switches to a strike slip, and then at depths greater than 3 kilometers, we have a normal faulting regime. So in the examples that we carried out, we assumed a kind of transition between strike slip and normal faulting regime, where SH max is equal to vertical stress, and SH min is half of the vertical stress. So condition for a slip on a fracture can be easily calculated as a function of principal stresses and their orientation relative to the fracture and the friction angle on the fracture. So here, this condition are expressed in terms of fraction of the vertical stress. So both in situ horizontal principal stresses are expressed as a fraction of vertical stress, and then also the pore pressure as well. So the critical pore pressure in order to create the slip on a fracture needs to is expressed here. However, if you want to have hydroshearing without hydraulic fracturing, this critical pore pressure also needs to be less, in very crude terms, than the minimum principal stress. So it is not guaranteed that we have a window for the critical pressure that allow us to create hydraulic shearing before we create the hydraulic fracture, and that is function of in situ stress state, level of deviatoric stress that we have in that in situ stress state. It is function of the orientation of the fractures relative to the principal stresses and also of the friction angle. So here we carried out just a relatively simple back of envelope calculation as a function of different friction angle. We kind of calculated the critical pressure, and then also this horizontal line is basically a line which corresponds to pressure equal to the minimum principal stress, which would be roughly again pressure required to propagate hydraulic fracture. So basically what we see is that, for example, for the angles which are less than 30 degrees, even for friction angle of 30 degrees, we wouldn't be even able to produce hydroshearing before we propagate hydraulic fracture. So the optimum orientation of fractures for hydroshearing then would be between 30 degrees and 90. However, when we stimulate the fractured reservoir, it is desired to stimulate more than one fracture set, because we would like to create a network of stimulated interconnected fractures. So it would be favorable to basically have a orientation of two sets where the critical pressure is roughly similar. So basically, as indicated here, for creation of interconnected network of the fractures from two sets, it would be favorable to have one set roughly at 40 degrees and then the other set at 80 degrees. So after the stimulation phase, we can measure area where the fractures have slipped, areas where the fractures aperture have changed, and so on. But those are just qualitative measures that do not necessarily tell us exactly how the stimulation will work during production. So the best way to actually evaluate different stimulation scenarios is actually to simulate the production phase. So the production was simulated at the end of the stimulation phase. We would assume that pore pressure dissipate allowed fracture to close, and then only those fractures which have slipped, experience hydroshearing, would have some kind of residual permanently changed aperture. And then we would carry out simulation of production phase, assuming different positions of the production well relative to the injection well. And during production phase, we had to conduct fully coupled thermohydromechanical calculation, and typically we would carry out those simulations for periods between 3 and 12 years. And with simulation of production phase, we were able to quantify, what is the fluid recovery, what is the injectivity, pressure required to basically percolate certain rate of the fluid through the formation. And then we could also quantify the produced temperature, how it changes with the time, and then also the produced energy as a function of time. For this model, we had to actually simulate also different forms of heat transport, including advection of the heat by fluid percolating in the fracture, heat exchange between the fluid and the rock, and then heat conduction in the reservoir, in the rock mass. So this part was actually carried out by coupling UDEC with the Python module. And one of the reasons that we implemented this coupling this way was to actually make entire process more efficient. Considering different processes, including mechanical deformation, fluid flow, different forms of heat, modes of heat transport, they occur in vastly different time scale. So running all these models perfectly in sync would be incredibly time inefficient and time consuming. So we had to make certain assumptions. For example, that solid model is always equilibrium, that flow model is always in steady state. And the time scale was actually coming just from heat conduction. So the Python module would carry out the heat conduction within blocks, heat advection. It would transfer temperatures to UDEC model. Temperatures changes as a function of time would result in additional deformation, changes in permeability, and so on. That would be resolved by UDEC, and then UDEC would then update those apertures back into Python model. So we would then advance this model in a time. So using these models for both stimulation and production, we were able to carry out a number of sensitivity analysis, including looking at the effect of different geometric characteristics of DFN, level of connectivity of the fractures, the fracture size distribution, their orientation with respect to principal stresses, investigated the effect of in situ stresses, dilation angle of natural fractures, in situ fracture aperture or permeability. Then we look at different operational parameters, design and operational parameters, including well positioning and spacing, injection rate, and viscosity. Now, to go through all of these sensitivity studies probably would take me half of a day, which obviously we don't have. So I'll just talk about maybe two. So one is looking at the characteristic of DFN. So when we generated DFN that we simulated in these models, we first assumed that we have two sets and that both sets are optimally oriented considering the potential for hydro shearing. What we realized really quickly is that in order for hydro shearing to have a chance, we need to have kind of fully connected DFN. And for that, we came with this concept of the cluster of the fractures, basically representing group of fractures which are connected with each other. So to have a fully connected DFN, we needed this cluster which kind of extend throughout the entire model. So the coloring scheme here actually indicates different clusters. So you can see there is one red kind of going from one side of the model to another, green as well. And then when we generate these fractures that represent DFN, we also want to make sure that the in situ aperture of those fractures is such that it represents realistic permeability. So we are able to carry out like directional permeability tests that would then give us, you know, anisotropic permeability field, you know, for the given assumed DFN. So when we have a characterization of the fracture network, we look at the fracture orientation, typically represented by a stereo net plot. We look at the fracture density or fracture frequency. There are a number of different parameters. The parameter which is most difficult to determine is the fracture size distribution. The reason is that typically we just cannot see the size of all fractures within a DFN. And typically it is assumed that fracture size distribution follows the negative exponential power law distribution. And this factor alpha varies typically between 2 and 4. So what's happening is that as alpha, so here is the chart kind of showing typical distribution of the fracture size or number of fracture or frequency of the fracture as a function of fracture size. So usually we have large number of small fractures and relatively small number of large fractures. As alpha increases, the number of small fractures increasing and the number of large fractures decreases, or probability of large fractures decreases. When we do modeling, of course, we cannot represent every single fracture in a model. So typically what we assume that there is some kind of threshold below which we assume that those fractures are not connected or do not affect the model results. And then there is also another limit, which is the maximum fracture size. So here we generated 3 cases, 3 DFNs for different values of alpha. However, for the first case, we also implemented the maximum fracture size to be 250 meters, given the model size that is 1 kilometer edge length. So putting this limit of 250 meters kind of completely skews the fracture size distribution. So instead of actually having largest probability of having relatively long fracture, actually this case ended up to be a case of relatively uniform fracture size distribution. So the top row actually is showing just the DFN with the fractures colored by their length, meaning that blue are relatively short fractures and red are long. And then on top, on the bottom, we actually show the contours of the fractures aperture at the end of the stimulation and after the dissipation of the pore pressures. So basically, so the reds, so the contours are apertures. Red is basically stimulated fractures, blue are unstimulated. So what we see that in this case one, actually, it seemed qualitatively that we have good stimulation because we were able to stimulate a certain volume, and the stimulation is carried out in such a way that we have a kind of network of connective fractures. As expected, the case for alpha equal 2.5, what we see where basically between these 3 cases, there is largest probability of having these large fractures, that we have this effect of localization of the flow and the formation, and definitely type of stimulation that would not be desired. So then we take these cases and then we run the production. And here I'm going to run the animation, and this is just for a case 1, basically showing the evolution of the temperature in the rock mass as a function of time. So basically, in the middle is the injection well, and those two red ones are production wells. So what we see is that one production well, although we put it inside the stimulated area, doesn't produce fluid at all. And I have to admit that this is definitely exaggerated by a 2D model. Basically, probability that some of those wells don't produce at all. But interesting thing is also, if I go again, the effect of secondary stimulation, that basically what we see that some of the flow paths are opening during production as a result of deformation caused by temperature changes. So then we carried out similar simulation for all three cases, and they're summarized here, and they're showing produced power as a function of time. So as expected, qualitatively looking at that plot of residual aperture or stimulated fracture network, case one is producing the most power, and then with for case 2 and 3, we do see this dramatic temperature drop. Now, if you look at these curves, you see that they're kind of going up and down, and the reason that they go up and down is a consequence of the secondary stimulation. So the next, what we did, we took this case one of first favorably oriented fractures, and then also favorable fracture size distribution. And then we carried out kind of more extensive sensitivity study of the effect of well positioning, but then also the relative, in terms of both distance, but then also orientation. So if you can see here, the well in the middle of the model is the injection well. The second well is the production well. So the top row is showing three cases of relative position of the production well relative to the injection well. So the first case is the position of these two wells are along the primary fracture set. The case two is that position of these two wells is along the secondary fracture set, and the third case is somewhere in between. So then we also carried out exactly the same analysis for well spacing of 500 meters and 800 meters. Yeah, of course, in numerical model, you can do whatever you want. And if you design EGS, you'll definitely not place two wells at 800 meters spacing. And actually, numerical model, it kind of shows why you don't want to do that. So here's the summary results showing the temperature contours in the rock mass after 32 months of production for these 9 cases. So what do we see? So first, 2 cases with 800 meters well spacing don't produce fluid at all. So that means if we increase the well spacing, of course, probability of losing fluid and not producing is increasing. And then I'll point out of 2 extreme cases among the others that actually produce the fluid. So the first one is case 1 for 250 meters well spacing. Basically, injection well, production well are basically along a single primary fracture. So what we see here is kind of localization of flow and deformation. The other extreme is the case for 800 meters well spacing that produce the fluid, where we do see quite tortuous flow path between the injection and production well. So all of these results are summarized in these charts in terms that are relevant for the performance of the EGS. And the charts are again quite messy, but I'll kind of point out some important results. So here on the right side, we have history of temperature and power as a function of time, and on the left side is injection pressure. And injection pressure is important because that controls what is the energy that we need to put in order to percolate the water at a given rate. So pressure is in certain way inverse to injectivity, which is a very important parameter for operation of EGS. Okay, so now those 2 outliers that I pointed out in the previous slides in terms of temperature and power are clear. So here is the case one for 250 meter spacing. So basically what we see, immediate temperature drop and relatively a poor energy production. On the other hand, the 800 meters well that produced the fluid shows very little temperature decrease and also very good performance. But then related to that, the case that showed short circuiting indicates very little pressure required to percolate required flow rate. On the other hand, the other cases, including one with 800 meter spacing, requires much more pressure, meaning that nothing comes for free. So if we want to produce energy, it is necessary, the injectivity will necessarily decrease. We need higher pressure to percolate the fluid at a given rate. So this is very coarse kind of summary or averaging of those results. So we averaged power over 500 years, and in these almost ideal perfect conditions, so the 2D model gives us results for 1 meter thickness. So those are the results of the model. So we assume that conditions are same for 300 meter thickness of the entire reservoir, which is, quite questionable. So under all these perfect conditions, it appears that, we could, given the different designs, we can produce between 15 megawatts and 35 megawatts. Now, as I mentioned, the increase in produced energy comes at the cost at lower injectivity, meaning need for higher pressure in order to percolate. So those trends are kind of summarized in these two charts. Okay, so conclusions, not only from these results that I discussed and presented, but also from all other sensitivity studies, that relying only on hydro shearing for design of EGS, I think involves significant uncertainty. And in order for EGS to work or potentially be economically viable, if you only rely on hydro shearing, there are a number of different things that need to be favorable. First, we need to have in situ stress state with sufficient deviatoric stress. We need to have multiple fracture sets with favorable condition of slip, meaning favorable orientation, and with a similar permeability. Typically, in order for EGS to work, we need to have relatively uniform conditions. Uniform conditions in the initial fractures size distribution and other parameters. Any heterogeneity, non-uniformity would favor localization of flow and deformation. That is certainly not the outcome that is desired with the design and operation of EGS. And then what we saw in the last results is that the temperature drawdown and injectivity are in different ways controlled by length or tortuosity of the flow path. So meaning that design of EGS would be a process of optimization of basically achieving certain permeability or injectivity, but in such way that we can also don't have too fast temperature drawdown. Okay, so this is what I plan to present. And so I have some questions. So first is from Varun Gupta. Are we looking at the projection of vertical fractures on a 2D horizontal plane? Yes. Yeah, that is the assumption in the model. Next question is from Chen-Ho Lee. In your experience, do you encounter many EGS that two favor-oriented fractures can be shear stimulated? Does the perm enhancement allow always follow the regional major perm? Does the perm enhancement all follow the regional major perm direction in terms of permeability tensor? Yeah, unfortunately, I'm not sure that there is enough. I certainly don't know, and I'm not sure that there is enough data to kind of answer your question. And again, as I said at the beginning, that's a kind of challenge with EGS, similar with oil and gas reservoirs. I mean, the only way to interpret the effect of stimulation is maybe, well, first looking at the pressures and then also on the microseismicity. And I'm not sure that that data would be sufficient to basically tell us if we are stimulating only one set or multiple sets. Do you have statistics of depth of current and prospective EGS projects comparison with oil and gas? I don't have statistics, but I think they're probably at a greater depth than oil and gas, but maybe if somebody else who is online knows better can correct me. What ranges of Mertic are talking about in geothermal reservoirs, and what is the range of permeability when you account for the natural fractures? I think, again, these are relatively low permeabilities. I don't want to now use any numbers. I'd like to actually come back and to give you a range of numbers, but typically we always select, when we create a DFN, we make sure that the apertures of a DFN are such that we match the in situ permeability. So I'll get back to you with the typical ranges of reservoir permeability. I don't want to put a number there that I'm not certain. What do you think are practical implications of this work? Is there a change in the modeling approach that you would do next time? I don't think I would change the modeling approach. I think practical implications are what I mentioned in the conclusions. I think designing EGS relying only on hydroshearing would involve significant uncertainty. And I think the optimum design should probably involve both hydraulic fractures and EGS. The challenge would be then, and that is question of improvement of technology, is how to keep those hydraulic fractures open, how to probe them, given the temperatures and the time of the expected operation of the EGS. Would you recommend stimulating EGS in Excite? It looks like production part. Yeah, so Excite is another software, Itasca software that was developed for simulation of hydraulic fracturing in naturally fractured reservoir. I think yes. And Excite would allow us actually to carry out these models in 3D. Did you mean that continuum theories would not apply? If so, what is the problem with suitably accounting for? So what is the problem with suitably accounting for instabilities localization in continuum framework? Well, I mean, they're not. I mean, I think probably it's possible, but I don't think continuum framework is really suitable for representation of discrete medium, particularly where there's probability or possibility of localization of the flow and deformation. It might be possible, probably wouldn't be the most efficient way to model those kind of processes using continuum framework. What are the boundary conditions on the perimeter of the UDEC square domain? In other words, what is the mechanism of heat supply to UDEC supply? So we keep the constant pressure and constant temperature at the outside model boundaries. Is horizontal weld being considered to improve injectivity and conductivity? Well, I mean, yes, we did as a part of this project and this study, we did analyze and simulate stimulation using horizontal welds. And in my opinion, I think that's probably the way to go forward, or that would be probably most efficient way to stimulate these reservoirs. About the directional permeability, are these simulations or lab tests? Is it published? Yeah, those are actually simulations. No, it's not published, but there has been a work by some other people who actually use UDEC to carry out these directional permeability tests. I think Ki Bok Min from South Korea actually published some papers and did some work on this. Does the shear of asperities not work against shear propping mechanism? Is there any evidence of comminuted material in cores, for example? I think the shearing asperities versus propping is also a function of confining stresses. I mean, at certain confining stresses, yeah, the shearing is definitely possible. But in this work, we basically assume that shearing doesn't occur, that it's actually roughness results in a fracture propping. Besides fracture shearing and opening, do these models consider dilation? I don't understand. Besides fracture shearing and opening, do these models consider dilation-induced bulk rockets max permeability enhancement? No, they don't. So basically, bulk in these models, blocks are basically elastic.
Branko,
go ahead.
Sorry to interrupt, but I just want to use
questions keep coming.
This is very good. This is very good. Actually, Andy mentioned that Branko, if you're available, stay in this meeting room and continue answer the questions, interacting with the folks. Okay. But I just want to say thank you, Branko, and especially Itasca, for sharing this frontier research on hydraulic fracturing geothermal. As I see this presentation, I couldn't help thinking of my industry, the petroleum industry, that especially for unconventional, when we go through the process of trial and error, wouldn't be nice if we have this simulation done at the very beginning of the unconventional development, so that we can save tons of efforts. But nevertheless, thanks, Branko. And for the folks who remain in this room, next week we will host Dr. Igor Dantsov. He will share another important aspect of hydraulic fracturing. It's basically the inputs for hydraulic fracturing. We especially consider heterogeneity and the layering lamination properties variations. So his talk will mainly focusing on how to generate rock properties for hydraulic fracturing modeling inputs. stay tuned. We will announce more details in the newsletter. For the folks who have not received my newsletter, feel free to send me an email. I will add you to the list. With that, Branko, feel free to take over and stay in this room. And for the rest of folks, we wish you, hydromanufacturing community, as well as ARMA, wish all of us stay well and healthy as the office reopen. And this is a challenging time. We've been through so much, and we just need to keep our alert and stay well and healthy. Okay, Branko, feel free to stay in this room. Thank you very much, Branko.
Thank you, Gang. Thank you, Gang.
Sure.
Okay, so I'll continue. I'll continue answering these questions. So the next one is, could you simulate hydraulic fracture propagation during injection? Is there any difference between hydraulic fracture and natural fracture in simulation? Yes, so I mentioned in one of the slides, so there is a horizontal cut that was perpendicular to SH min that was representing potential trajectory of hydraulic fracture. The limitation of this model is that hydraulic fracture had to be confined to that cut. Yeah, and there is difference between hydraulic fracture and natural fracture in the sense that natural fractures are, you know, already broken, so you know they have certain shear strength, either just frictional or some cohesion, while the cut for hydraulic fracture is kind of bonded together, and then it opens during simulation as dictated by the stresses ahead of the fracture tip. Also, why choose valves parallel to fracture? This seems like a worst case concept. We agree, and you know that was one of the limitations of the to the approximation. We kind of realized that, and consequence of that is also greater sensitivity of this model to and prediction of fluid production to actual location of the well. So if well would be moved, you know, just a little bit, you could have either producing full injection or completely losing a fluid. I think the enhancement is coming from the connectivity of the fracture. This is difficult to achieve unless fractures are long enough to connect to each other, or via hydraulic fracture to connect to these natural fracture. Where comparison between your UDEC models and field, I kind of agree. I agree that it's important to have a network of connected fractures and be able to actually stimulate increased permeability of all sets involved in the network, and that there are a number of advantages of having hydraulic fractures, including allowing access to DFN further in a reservoir. No, we haven't had a chance to compare or validate the UDEC models with the field production data. I mean, we hope maybe during the Utah Fort project that we will have opportunity to do that. There is this difference between the two horizontal stresses in a strike environment, which would force the hydrofrac to go in a certain direction. Do we expect slip of natural fractures? No. Do we expect slip of natural fracture in the opposite direction to SH max, so as to create a large compressed hydrofrac network? Yeah, I'm not sure that I fully understand. Do we expect the slip of so basically here in this model, we actually try to do stimulation of the discrete fracture network by hydro shearing using pressure which are below the hydraulic fracturing pressure. So, and that was possible because of the given stress conditions and orientation of the fractures and so on. Okay. So. Have you tested this model load boundary condition over lateral boundaries rather than fixed normal displacement? So I think, yeah, I think the model extent and so on is such that actually the difference between different boundary conditions, you know, either stress or displacement shouldn't be significant. And I think we definitely check that. I thought we rely on hydroshearing for low permeability in shale gas production. Do we rely on hydroshearing in EGS design currently? Well, that's definitely desire. However, I don't think that we can rely only on hydroshearing. Temp and injectivity change depend on fracture length or torsion. Do you mean they are equivalent? No, they're not equivalent. Actually, as tortuosity increases, the temperature decrease becomes less. On the other hand, the effect on injectivity is basically injectivity decreases as well. So the effect of the length of tortuosity is kind of on the temperatures or heat production, and injectivity is competing. Many HDR formations do not have sufficient natural fractures. Do your works and conclusion apply to those formations with very limited natural fractures? Well, that's the other reason why we can't rely just on hydroshearing, because in some formations, you know, there isn't enough pre-existing fracture network, or if there is pre-existing fracture network, they are connected or they're not permeable, and so on. So on the other hand, we can always count on hydraulic fracturing. One of the advantages for UDEC is to simulate multiple fracture. Is it overkill for EGS in HDR when natural fracture is limited? I mean, it's not overkill. I mean, we are just trying to find out what are the in situ conditions that would be favorable, for which there is a chance for EGS to be viable. Maybe those conditions, you know, don't exist. So next step would be, and that's what we always suggest. I mean, a first step would be to basically characterize the site, understand in situ stresses, characterize the discrete fracture network, and then based on that, it can be decided what is the best, what would be the best design or strategy. Would it be relying on hydroshearing, stimulation of existing fractures, or it would be necessary to create hydraulic fractures? Okay, so I think I came to the end of the questions, at least here that I can see. If you think that if your question was not answered or whatever, yeah, please feel free to send it directly to me, or maybe send it to Andy or Gang, and they'll forward it to me. I'll be more than happy to answer. If you also think that I didn't answer your question properly or didn't understand it, you know, please send it again or by email, and I'll try to answer again or try to clarify it. Okay, Andy.
Very good. Thanks, Branko. Really
Okay, you're
appreciate your
welcome.
time and for going through everything. And thanks to all of those who attended and stuck around. Really enjoyed the talk. So good to see you again, and take
Yeah,
care.
good to see you too. Thanks to everybody to coming to listen. Yeah.